All right, so question 26. A photoelectric effect experiment was conducted by shining a different frequency of light on a plate made of an unknown metal. The graph shows the kinetic energies of ejected photoelectrons with respect to the frequency of incident light. Before even going any further forward, we're thinking about photoelectric effect. I would like to probably think about what formulas might be apparent. And I know the one that's coming straight to mind is our photoelectric effect, a formula. EK is equal to HF. H is our Planck's constant, F is our incident frequency, minus W, and W is our work function. So our work function is the energy we have to overcome to actually eject an electron. So if we hit our incident frequency, hit the piece of metal with an incident frequency that nets a EK of 0, right? Exactly 0, not less than. We would be able to find out if we knew what our F is, we could rearrange it and solve for our W. So what we're going to use first of all is to, let's continue reading the question. I'm getting ahead of myself. But the table shows the work functions of various metals, determine which metal is most likely to be ejected by the photoelectrons in this experiment. So here we have our table before, or our graph. Our incident frequency is our x-axis, as our kinetic energy of our ejected electron is our y. Now, an important thing to note is our y is measured in EV. Remember, Planck's constant, it has joules as one of the units in the formula. So if we calculate anything in our formula right now, we will calculate it in joules. Or if we use any kinetic energy or any data from this graph, we need to remember the kinetic energy is in electron volts. So first of all, I want to find out when our kinetic energy is equal to 0, what was the resultant incident frequency? Now, at 0 electron volts is also the same as 0 joules. So here I'm just going to write a statement down here at our EK is equal to 0 joules. I need to find out what the incident frequency is, and in this case I'm going to say F. Easiest way and probably the most stress-free in an exam would be drawing a straight line or getting your ruler out, extending it through, and finding, okay, where does it cross the x-axis? Because when you cross the x-axis, that's when your y is equal to 0. In this case, it looks like it's probably sitting around about the 1.1, so that's what I'm going to go ahead with. So 1.1 times 10 to the power of 15 hertz is the frequency when we get an EK of 0. Now, another way to calculate that would be you could do the change in height or the change in y over the change in run or the change in x. So we're just thinking about a simple y equals mx plus c. Our gradient in this hand would be the change in EV volts over the change in incident frequency. I'll just call that IF in this case. You could find the gradient and then you can substitute C in by, say, picking a point like here at a frequency of, incident frequency of 4 times 10 to the 15 hertz. You get, it looks like 12 EVs. And then that way you could then solve for when y is equal to 0, what is your x function here? But under exam, getting the ruler out is probably the quickest way and the easiest solution, because what we're looking for is what's the closest. We're not looking for an exact value in our solution for this one. If we scroll down, we are just looking for a statement for what metal. What is the metal we're working with? So let's continue our working. So the frequency is 1.1 times 10 to the 15 hertz. Cool. Let's write out our formula. So EK is equal to HF, Planck's constant, minus the work. So the reason we're choosing 1.1 is because at 0, HF, or our Planck's constant now, which is 6.626. That's in your formula book, times 10 to the negative 34, multiplied by our frequency, 1.10 times 10 to the 15, minus W, our work function. We can end up solving this as W is equal to, we're just going to change W over to the other side, simple algebra. And we end up getting our work function equal to 7.29 times 10 to the negative 19 joules. So remember, Planck's constant has joules as one of the units there. So our answer should be in joules when we get our work function. The next step left is we need to find it in EVs, electron volts. So to convert from joules to electron volts, what we end up doing is dividing by 1.6 times 10 to the negative 19. And we end up getting 4.55 EVs. Closest one to 4.55 is copper. So my answer is going to be copper. Now, if you're stuck with figuring out the conversion from joules to EVs, this 1.6 is in your formula book. It says that 1 joule is equal to 1.6 times 10 to the negative 19. All right, that's question 26.